Awesome. Thanks for joining us, everyone, for Archive Dives with Oxen.ai. Archive Dives are deep dives into archive papers. There's a lot of gems of knowledge hidden in these research papers, and the main motivation is to find them, keep up with the latest and greatest in the field, and make us all smarter oxen. Today, we're going to be going over the segment anything paper from the team at Meta. And this is really a foundational paper for computer vision. There's been a lot of research in the natural language processing and LLM space to make large language models that are trained on web scale data. And really the goal here with the Meta team was to collect a web scale computer vision data set and use it to do a pretty foundational task in computer vision, which is segmenting out portions of an image, but being able to segment out anything in the image. So traditionally, these models can look for humans or horses or chairs or tables. There's usually about 80 categories of things that these models could extract. And the idea behind this paper is just being able to segment out anything. So I thought it'd be great to start with a little demo video. This is a real-time C++ library that was built to run the model. You can see they're just clicking on points in the image, and it's segmenting out a mask of that specific, trying to figure out what's around the object and put a mask on it. So you can also think of this like when you're in Photoshop and you use the lasso tool, it's trying to do that automatically and just save a lot of time. And this is a pretty complex image. So the fact that it can do hair and just the specific portion of the guitar is pretty interesting. And you'll notice it takes a second to like initially load the image, but once the image is loaded, it's really fast to go through and find the thing that you want to segment out. So that's kind of the high level, what are we going to be doing? And I think it's helpful to have some background knowledge of just like use cases of why would we do this at all. So like I mentioned, you can think of it like the lasso or brush tool in Photoshop. So you might be familiar with that. You literally have to click on each pixel here that you want to mask out, and it takes a minute or two for a human to click through this, and they actually have a very extensive labeling process that we'll go through of how they did this. And there's a lot of different use cases for this. You can even see it right now for Zoom meetings. They use similar technology just to segment out the person and maybe even their dog into the foreground and then blur out the background or put a virtual background. This is important for the self-driving car space. So knowing where the road is versus the sidewalk versus the maybe pedestrians that are crossing the street, this would be a pretty complex segmentation mask where they're doing all of that at once. So if you're in your Tesla, this is kind of what they're trying to do real time. Image editing, there's a lot of software coming out these days that is using this technology to make it really easy to do like a green screen type effect, kind of like the Zoom background that we saw before. And you can see that same process of like clicking on 2 points of the person, it automatically segments them out, and then you could put whatever you wanted in the background. You see this all the time in live television or sports. So you'll see, for example, technologies applied on this volleyball court where they're segmenting out the people and they're putting an advertisement at the bottom. That's probably not the most fun use case, but even when you're watching an NFL game and they put the first down line on the field, or they put the scoreboard on the field under the players, that's running real-time segmentation. And then finally, augmented reality. There's a lot of new tech popping up for this. This is probably a big reason why this paper came from Meta and Facebook, because they have a big push for augmented reality. And I don't know why that image didn't come in, but some loading problems here, I guess. You can imagine placing an object in a scene that's occluded by a person while you're looking through glasses there. You could also imagine like robots going through a store and collecting things off of shelves. They have to know exactly what is in that picture. And honestly, I might just pull up my side notes here to get these images, because I think they're pretty helpful and pretty illustrative. Let's go to my side notes. Okay, so this is an example of the augmented reality stuff. If you were just to naively put that 3D model on top of the person, obviously it doesn't look like it's in the correct place in the scene. You can see that with the Pikachu right here, being able to put it so it makes the scene look realistic. This would be an example of maybe an inventory check of a robot going through a store and counting the actual items. Or you might actually be doing this with satellite imagery, trying to find wildfires, flooding, weather patterns, etc. So there's a lot of use cases for this technology, and I think it's great to kind of call these out before we dive into the rest of the paper. I do believe that Notion is much easier to see from the text perspective, so it looks like it's loading again, and I'm going to switch back to that. All right, so the segment anything paper itself, Meta introduces this model along with a data set of 1 billion masks on 1 million licensed and privacy respecting images. So if you look at this image above, you can kind of see where that ratio comes from. There might be one image in here that has 100 things segmented out. So 10 million times 100 is about 1 billion masks. And they really don't want to limit themselves to a category of things. They really want to be able to segment anything within the data set. So we've seen these foundation models in LLMs where, you know, GPT-2 and GPT-3 were trained on a web scale data set of text, and they really want to make this web scale data set for computer vision. And we've already seen this successful for things like DALL-E and Stable Diffusion or Midjourney to generate images. This is just kind of like a different task with a different data set. So there's 3 components that they dive into. There's what they call promptable segmentation. There's the model architecture, and then there's the data that went into building it. So what they mean by promptable images is we usually think of prompts as text, like typing in segment out the person in the image. But what they really mean by prompts in this is threefold. One is just clicking on a point in the image, and they're saying that's a prompt. Or you might just draw a bounding box around the thing you want to segment out, and that's a prompt. They also allow text prompts, but they kind of do it in this threefold fashion. And it's just important to recognize that there's different things that they mean by prompting in here. And they also mention that prompts can be ambiguous. So just because you clicked on this part of the backpack, do you want just the zipper, or do you want the full backpack, or do you want the person that the backpack's on. So there's really like 3 levels of things that you might want to segment out. So the model has to take that into account and kind of give you different options of what the person might actually want to be segmenting out. So they give the example of clicking on a point in the shirt. Do you want to segment out the shirt or the full person wearing the shirt? So the model itself consists of 3 parts. There's an image encoder, which is a neural network that takes in an image and puts it into embedding space. And then there's a mask decoder, or sorry, there's two inputs. There's the image encoder and the prompt, which both get encoded into vectors. And then there's a mask decoder that takes all of the information from the image, all of the information from the prompt, and tries to generate a mask. And you can see here, they're generating 3 potential valid masks for this one point that they were prompted for. So is it the left part of the scissor? Is it the right, left and right, or is it the full scissor, for example? And they really architected this model so that the first half can be relatively slow, like maybe it takes a second to encode the image, but the second half they want to be really fast. So encoding the prompt and decoding the mask, they're talking about this user workflow where they wanted this half of the neural network to run within 50 milliseconds to make it feel real time. So the user can just kind of like click on different parts of the image and it automatically segments out that thing. One of the big portions of this paper is just the data set that they collect. They call it the data engine. And if you think about collecting 1 billion annotations on 11 million images, that takes a really long time. And there's a lot of ways that you could go about that. So they kind of do it in a 3-step process. One is what they call assisted manual, where they have a human and a computer vision model working together, where the model will suggest a mask, and then the human literally goes into a tool like Photoshop and uses the eraser and the lasso tool and really like fine grains that mask itself. So that's a big portion at the start. Then they have the second portion that's called semi-automatic, where they prompt the model that they trained in the first step with just like random likely object locations. And so you can think of just like finding bounding boxes on the image and do a second step of having the annotators annotate, but the annotators have to annotate less in this step because they did a lot of work in the first step. And then finally is this fully automatic step where they just prompt the model that they trained from the first 2 steps with a regular grid of foreground points, not limiting it to any object class in particular. And this is where they get about 100 masks per image. And this is how they really scaled up from the data sets that traditionally are like 100,000 images and 800,000 masks to 11 million images and 1 billion masks. It's really this fully automatic step at the end.
Hi, okay, sorry, popping. I'm sure it was in there, but I don't remember seeing it. Like, what kind of validation did they do on those additional auto-generated masks, just to, check that nothing's going off the rails with that, or did they?
They did. So at the end, they actually do a lot of interesting analysis on this. And let me try to find in my notes. They said for that final step to estimate mask quality, they randomly sampled 500 images. And maybe I got the math wrong. No, that's right. 500 images with like 50,000 masks. And they asked the annotators to go back and validate the quality by annotating them again. And they do this through just kind of like a computed overlap between what the annotator said and what the model said. It's called IOU is like the technical term for it, for the number. But yeah, there's no way that they can go through all billion masks.
For sure.
And so they kind of did this for the 500.
Got it.
Cool. Great question. These are some crazy examples of what you might see. So you could imagine like a sports game where they're segmenting out every single individual seat, a bazaar where there's a marketplace and they're like segmenting out every single grape in the background. Like these things get pretty complicated, or it kind of goes from, you know, less than 50 masks here, 50 to 100 masks, 100 to 200, and then these images have over 500 masks within them. So like we said, there's multiple data points that they take as inputs and outputs. The input is a prompt, which could be a point, a bounding box, or a piece of text, and the output is the mask. And so what they do is they have an original data set, and there's some classic ones in the computer vision world. There's one called Coco or MS Coco that has about 123,000 images in them. And all those images are already labeled by the community. And they're labeled by, they have the image and the bounding box and the mask and the label. And what they do is for that first step, they generate a new data set that is for each one of these things. You can think of, okay, well, they already have a mask around that image. So they generate a bunch of image prompt pairs that is like image 0.1 mask. So they just pick like a random point within the mask and they pretend to like a user would have clicked there, and that generates a bunch of new pieces of data for this more prompting style. They do the same with the bounding boxes from this original data set, and then they do the same with the labels from this data set. And the labels might be something like 80 different classes, and this image right here has the category of hot dog. And so they generate a label that says like, segment out the hot dog in plain text. And then that's the training example. And so for the assisted manual stage, which is that first stage of the data collection pipeline, we mentioned that they have the annotators that go through and kind of use the brush and eraser tool to improve the masks that came out. But the annotators were giving no restriction for object classes. So they could freely label and did freely label stuff or things as one of the classes, which is traditionally not something that you would do in this style of data set. Like this one that we pulled up here has 80 different object classes, ranging from airplane to apple to backpack to banana, etc. It's a much more fixed and limited set of examples. And so what they said is they asked the annotator in order of prominence in the image to mask out these things. And if it was taking them more than 30 seconds to annotate a single image, their tool just told them to move on so they could quickly get through as much of this as possible. And so their initial model is kind of trained on a data set that's very similar to this size. They didn't link to this specific data set, but it's kind of like a baseline one that they had all these annotators help them fine tune. Then during the semi-automatic stage, This stage aims to increase the diversity of the masks so that the model can do even more. They loop the annotators back in and presents them with the new masks that they trained the model to detect here, and said, okay, now that you see all of these ones, go find all of the objects in the small corners, things that we didn't annotate in the first round. And so it's just, this is kind of the full step of trying to increase the diversity. And so in this stage, they collect another 5.9 million masks on a new 180K images for a total of 10.2 million masks. So just acknowledging that there's a lot of work that Meta did in these stages, and it's actually pretty impressive that they just released all of this to the public afterwards, because it's not, you know, financially, it's pretty expensive. The fully automatic stage, they prompt the model with a regular 32 by 32 grid of points and just have the models that were trained from these first two stages try to segment anything. And this is the process that goes from a small data set to the large data set. So we go from, what did we say, 180K images to they just had 11 million images that weren't annotated, and they ran this model on them and produced 1.1 billion high quality masks. And as they're doing this, they calculate how confident the model is in the masks. And they, you know, if you have ambiguous situations, they kind of average the predictions and do some fancy filtering techniques for what they call stable masks to just return the most high probability ones. So the model might return 300 masks for an image, and they actually filter that down to 100 high confident masks. And what's really cool after they did this process is they kind of did an evaluation of the different data sets and where the center of all the masks were within the images. And so the Coco one that I showed you before, most of the objects that were annotated were really in the center of the image, which makes sense because that's just traditionally the focus of an image. And with their SA 1 billion data set, you can kind of see how it spreads out much more evenly, and they have masks for things in all parts of the image themselves. But it's important to note that like 99% of the 1.1 billion masks were generated automatically in that last step, and there was no human intervention there. At the end, they talk about fairness and responsible AI while they're doing this process, and they really emphasize that they're trying to make a data set that is represented of geographic regions, income distributions, and they've just noticed in general that like some countries or low income countries might be less represented in this data set, and they're trying to at least do some sort of analysis to let us know where these images came from. Let's not all have them from the US or China. Let's try to make a more even distribution. And so they didn't get all the way there, but they said it was a good step in the right direction. They also did some analyses across perceived gender, skin tone, and age group, just to make sure there's a good balance of men and women in the data set, older, middle-aged, young people, and just a good representation of all skin tones. They evaluate it on, there's actually 23 other data sets that they evaluated on, Ben. I forgot about this as well. So there is some like gold standard data that you can do this against. And these are some of the names of the data sets for reference. And they have some of their scores on there, but they say that this SAM model outperforms a lot of the models that are out there, even on a subset of labels that are in that data set. So it's pretty impressive, and just like another reason why these foundation models continue again and again to be more powerful than your base one, just because they've seen more data. This thing's like seeing 11 million images versus the model that's only seen 100,000, and seeing more and more examples makes you generalize better. So wrapping up, just I think it's really cool that Meta did all of this work, open sourced it. It's a non-trivial amount of work, and now more applications can be built on top of this foundational model or the foundational data set. They mention at the end of the paper that these models and data sets are very composable. So say you wanted just to do the person segmentation, or you wanted to do something very specifically for dogs and cats, or very specifically for self-driving. They're like, hey, we're releasing this data set so you can slice and dice it. We're releasing this model so that you have a good starting point to build your more specific application. And I think a really good example of this might be, say you wanted an entire pipeline to run real time on video, like they do in live TV or whatever it might be. This model itself takes about, and you saw it in the demo at the start, the second half of the model runs at 50 milliseconds, which means you could only really do like 20 frames per second on a video. But the first image encoder step still takes half a second to a second. So you can't really run that first step in real time. So if you wanted to train a much smaller model that was really good at just detecting things in your self-driving car use case, and you want that to run at like 10 milliseconds total for the entire pipeline, you can't do that with the model that they released, but you could do it with the data set and filtering it down to exactly what you wanted the model to do, and just like distilling and fine-tuning. So we've already seen, like, this paper came out in April of this year, and we've already seen the model been put into production in a lot of like Photoshops or Runway ML, or I imagine a lot of the self-driving car companies are using at least part of this data set or some learnings from this model to improve theirs. But just really think it's a cool thing, and excited to see what people build next. And I'd love to open it up to the floor for just, I know, Ben, you've worked on a lot of satellite imagery. Jennifer or David, I don't know what your background is, but if you've worked on computer vision and see cool use cases, so to just open it up for discussion.
Yeah, so I'm doing my master's in computer science right now. So most of my experience has been like class project based. Did some work with satellite imagery, and this would have made things so much easier. Kind of wish it existed then. But yeah, I'm so curious like how Meta might be using this internally. Like I'm wondering if, I guess everyone must have seen like the whole metaverse recent update. Like I'm wondering if this helps them with that. Like what's their incentive for releasing this? It's kind of incredible that they did. So yeah, kind of curious what they might be using it internally for. And also like how this might extend to like how specific can things get? Because like now I guess it can segment to like what is a boat, but maybe it can detect like how specific of a boat it is, like maybe the actual type of a boat. And I'm wondering like what's the next step in using this towards something like that? Those are my two thoughts right now.
Yeah,
great
totally.
Great overview. Thank you so much for doing that. Really helpful.
Yeah, no problem. I think, and this is me just guessing in the dark, I think a lot of the like open sourcing part of this from Meta's perspective is it's really great PR, like you said at the start, and it probably helps them recruit really smart engineers as well. And then I think internally they probably have so many different versions of this data set and versions of the model that are like I said, for their glasses use case, you might need a very small model that can just like really do people really well, because that's the most important thing that they want to like have that Pikachu run behind your legs or something for a demo. So I imagine they're doing a lot of like fine tuning from here and some secret magical sauce under the hood. But I love your idea of like a very specific boat one that could be used just for, I don't know, the Navy or like helicopters saving people, or there's so many applications I think that you could start letting your imagination run wild on.
Ben discovered secret Russian boats at some point in your prior job or something like that.
That's yeah, that's on the down low. But when I was doing satellite stuff a couple of years ago, like there was so much, we would build a couple of segmentation models that we would try to deploy kind of like anywhere in the earth, and it was like not even did we have to have a specific model for solar panels. We had to have a specific model for solar panels in certain continents and certain regions of the world during certain times of year. So like that level of granularity was just so cumbersome from a training cost perspective, and then from a data and model management perspective, that it's like super awesome that this is already, this seems like an enormous leap forward in that respect. One thing that I'm interested in, and I haven't gotten a chance to play around with it yet, but a lot of these like foundational models, like some of the ResNets for classification, struggle to generalize to satellite imagery. Jennifer, I don't know if you ran into that as well in some of your work, but it's like they're trained on, very high resolution stuff that's taken from a cell phone camera and is right in front of you. How do they work when you have, 10 bands instead of just RG and B, and every pixel is, the size of a football field? So I'd love to play around with that sometime.
100%. There's like maybe like 1 or 2 satellite data sets that you can use for pre-training, and then like that's it.
Yep.
Are any of you guys familiar with Skyfi?
No, what's that?
So it's a company. I'm gonna drop the link here, and I happen to know Bill Perkins, the founder, but I think that they have just started to open source some of their imagery. Which could, bringing worlds together, this could be kind of a game changer.
Yeah.
I'm gonna hit you up for intro because we're doing a hackathon with we're working on it now with XPRIZE around wildfire, so we'd love to talk to them a little. Very cool.
Yeah, the wildfires is a really cool use case because there's the satellite imagery portion of it, but there's also like an automated vehicle portion of it, of just like sending in robots to put out the fires instead of us, and if they can know exactly where the fire is versus not and segment out the image, that's like a real world use case that's pretty awesome.
And then you have kind of both sides of the coin that you were talking about earlier, Greg, where like you need kind of in your headquarters, you need the like very accurate, if a little bit slower models, and then when you dispatch your drones or whatever, they need to have some kind of onboard super fast kind of processing thing. So cool to use both.
When I was starting at machine learning in 2019, one of the main problems I encountered was the bias thing. I wanted to build a face recognition model, and this face recognition model used free data, but this data was mainly from Europeans or United States. So when I tested in my country, was really bad at trying to recognize these faces. Was like it worked better for people like have European faces or like whiter, but in my country there are all kind of mixes. So this new technology that generalizes and use a lot of data from all over the world, that was the most interesting part, MetaSay. It's helpful because this bias has always existed in this field. Like you download a free data set, but this data set is from other parts of the world, like China, United States, when this artificial intelligence stuff is more advanced. So it becomes really hard to find or make your own data set that works for your specific case. And this segment everything, it works really nice because you can use it, like, for example, take pictures of every part of the world and take any information you want. For every data set you want a data set of person, you take a random image for all over the internet and take only the persons that you're trying to network with that data set. So this is more like a zero-shot example of how you can build other data sets with this model, which is actually really great.
Yeah, I love that. I love that point. Have you tried the model itself? Have you clicked around with it yet?
Meta had, I don't know if it's still available, but they own demo which you can test for free. Let me check if it's still active. And it was really great. I haven't integrated it into a project yet because I have been more interested in this natural language processing things that is happening this year in particular, because this year is crazy. You have some, for example, you have natural language processing, you don't know where to put your attention. But ChatGPT, for example, now uses some vision for image that can know exactly in which part of the image is every tool. I think there is something like MetaSum there to help it works better than Google Lens, because Google Lens doesn't really recognize every part of the image like ChatGPT does. So this really interesting how there are many models that do basically the same thing but use other technologies. So some things are better than others. Let me check if I can share this demo.
Have you seen, I'm curious, because you mentioned like the computer vision half of the data sets not being balanced across the world, but I also feel it's the same thing with natural language processing, and there's just not enough data in Spanish or not enough data in Portuguese or whatever it might be. Have you found that as well? Well,
the thing with natural language processing is that you can make this thing go automatic semi-supervisor. So you take some data set of some random Spanish text, you take away some parts, and you make the model try to recompose these parts. So because it's semi-automatic, you only need text. You do not need labeled text or any specific kind of text. ChatGPT is very good in Spanish for this thing, but actually Palm 2 and all other models like Llama 2 are not that great with the Spanish, but I think it's something that the companies decided to do. Like, we are not gonna use this as a Spanish data set because we are not sure what can do to the model, because it could break some parts of the model if they write something in Spanish. While ChatGPT was like, let you just use a big data set of all kind of words in every language. And I haven't tested because I know Japanese too. And it's great for Japanese, English, Spanish, and almost all kinds of languages. While Google Bard, Palm 2, Llama 2 are really bad. Even in Spanish, they are really, really bad. Even Whisper is bad for Spanish.
Yeah, that's a good. There's like so many. I feel like there's so many ways that people can slice and dice data, and I don't know. People say models are so general until you dive into the details, and you're like, no, there's a lot of edge cases.
The world is not just the big companies like Meta, Google, and OpenAI. They are all in San Francisco, all in a little point of the world. You have to expand more if you want to make a general AI.
Totally agree. Totally agree. Cool. I see some of the links.
I've got to find the image for it again, but the funniest case of that was I forget which one, but like the little self-driving, self-delivery robot cars they were built in SF, and there's this amazing picture of a dozen of them in Boston, just all stuck in snow.
Yeah.
Forgot that little environmental factor.
Totally. Or there's so many ways that one might be more of a hardware issue as well.
Same as problem, like just not having a global mindset and you get stuck in the bubble.
Yeah, totally. Well, awesome. Thanks for joining, everyone. Feel free to invite your friends next time, and we'll be posting video on YouTube, the notes on our blog if you want to go back to any of the links or any of the images or anything like that. And it's just awesome to have like people from all around the world to get their opinions too, because I really appreciate that, Adam. Or David, sorry.
I have a bit of a random question. I was just going to ask Ben, what were you up to with the satellite imagery before?
Yeah, so weirdly the two internships that I did in school were both geospatial and satellite related. So my first job was at a company called Astrea that was focused on satellite like machine learning and data analysis specifically for like climate and sustainability applications. So we were doing a lot of kind of like site scouting for renewable energy developers, and then also kind of honestly very close to what Greg was talking about with the kind of drone dispatch. We weren't looking at finding wildfires for like putting them out via drones, but like post wildfire reforestation, we work with some companies that were like depositing seed packets via drones in specific areas. So it was a lot of fun, and definitely, as Jennifer mentioned too, just like an area of the computer vision literature that's still, like, as everything else is like completely blowing up everywhere else, there's still a ton of work that's being done, but not really as many foundational models and data sets, which is sad but fun. It means there's lots of work to do.
Super interesting.
Awesome. Any other final thoughts from anyone? Great. Well, thanks, guys. Hope to see you next week, and ciao.
Definitely. Thank you.
Bye. Thank you.